A huge thanks to Brilliant for sponsoring this video. More details about their offer later on. I love using animations, whether in my videos or other projects. Beyond just their aesthetic appeal, they can be a fantastic educational tool. But how do you actually create these animations? Is it complicated to program? In this video, I'll show you the method I personally use. And the great thing is, it's surprisingly simple. When I talk about animations, what I'm really referring to here are transitions. By that, I mean adding some movement between two distinct states. The process of adding data between two discrete points is called interpolation. The term might sound intimidating, but the concept is actually simple. Let's take the example of transitioning a number from a value A to a new value B. Without any interpolation, you'd see the value jump instantly from A to B. With interpolation, however, we introduce a duration for the transition. Typically, I use 1 second as a base. Let's now calculate the transition value, which we'll call C. To move C from A to B in 1 second, it needs to start at A and cover the difference between A and B. At any given time t, the value of C can be calculated with this formula. At t equals 0, C equals A, and at t equals 1, C equals B. However, this type of transition is quite basic, and there's plenty of room for creativity. Instead of using time as the direct ratio for delta, we can use a variety of functions that take time as a parameter. As long as f0 equals 0 and f1 equals 1, it will work. When we use the identity function, as in this first example, we're performing a linear interpolation. Let's look at a few other examples. You can find the equations for these functions on easings.net, which is an excellent catalog of transition functions. If we apply this to our number, we get a smooth transition. It might not seem very exciting with just a single number, but this technique can be applied to any kind of vector. That means we can use it to control things like angles, scales, positions, colors. Now that we've covered the basic principles behind animations, let's see how we can implement them in C++. We'll be using the SFML to handle the 2D rendering. It's the same library I use for my own animations, like the ones in this video. First, let's create a circle whose position is controlled by a variable named circlePosition. When the spacebar is pressed, this variable is updated with a new value. As expected, the circle instantly teleports to its new position. To smooth this out, we'll now implement an object that automatically handles the interpolation for us. This object will hold a starting value, a target value, and the timestamp of when the animation began. When the object is constructed, it is given an initial value. Next, we'll create a function to get the current timestamp. For this, I'm using chrono from the C++ standard library, but you could of course use any other time source. We will then use this function to calculate the time elapsed since the last value change. This method is used to update the target value. It defines the current value as the starting point, assigns the new target, and resets the start time of the transition. Using the elapsed time, we can now calculate the object's current value using the transition formula. As we saw earlier, transition functions operate on a 0 to 1 range. Therefore, we'll need to cap the elapsed time to ensure it stays within this interval. To make the object's usage more transparent, we also define two operators. The first automatically casts the object to its underlying type, while the second is used to assign a new value and trigger a transition. Thanks to this, all we need to do to use it in our example is change the type of the position variable. And just like magic, our circle now moves smoothly to its destination. Our current implementation has two limitations. It's locked to a 1-second duration and only performs linear interpolation. First, let's make the transition's duration configurable. To do this, we'll need a new speed attribute. We will use this to scale the elapsed time, which in turn will control the transition speed. Next, we'll add a method that converts a duration into a speed value. And that's it. We can now set the duration for our animation, in this case, to half a second. Now let's add the ability to use different transition functions. We'll start by implementing a set of these functions, along with an enum to identify them. A separate dispatch function will then select the correct implementation based on the enum's value. In our object, we'll need an attribute to specify which transition function to use. Then, we simply replace the t variable with a call to our dispatch function to calculate the current value. And voila! We can now choose the desired easing function for our animation. Now that we have a working implementation to hand, I'll show you two examples where adding animations can dramatically improve the presentation for very little effort. Let's start with a simple case. A set of draggable cards placed in a grid. All the cards are stored sequentially in a single 1D array. To place these cards onto a grid, we need to convert their array index into 2D coordinates. We'll do this using a row major order, which means we fill the grid one row at a time. You'll notice we start a new row every 3 cards, which corresponds to the width of our grid. This makes the calculation straightforward. An object's vertical position, its row, is its index divided by the grid's width. Its horizontal position, its column, is the remainder of the index divided by the width. This allows us to translate any index into its corresponding 2D coordinates on the grid. This formula provides an easy way to position the cards. To highlight a card, its scale increases slightly on mouse over. As a card is dragged across the grid, it swaps its position in the 1D array with whichever card it is currently over. Each time the array is modified, the card's positions are recalculated using the previously mentioned formula. Everything works well, but it's a bit abrupt. If only there were a simple way to make it all more dynamic. Just by using our awesome object for the card's position and scale, the whole set animates naturally. This is literally a 2-line change. Obviously, it can expand a bit if you're configuring the duration and easing function for the transition. Let's take a look at a slightly more advanced example, involving more complex interactions. Here, we have a prototype of a card game. They can be drawn from a deck and then placed either on the table or added to your hand. It's also possible to rearrange the cards in your hand and put them back into the deck. Once again, everything is functional, but the experience still feels quite rigid and choppy. Now let's see what happens when we use our automatic interpolation system in the project. That's where the magic happens. All we need to do is describe the instantaneous state of the objects. The transitions are handled automatically. There's actually a small trick involved with the card flipping effect. I used a flip variable that serves two purposes. It keeps track of which side of the card is visible, and it controls the scaling on the x-axis. By using its absolute value, we naturally create the illusion of a card flipping to reveal the other side. What's really convenient is that you can completely change the feel of the animations just by choosing a different transition function. The interpolated value code is available on my GitHub account. The executables and source files for both examples can be found on my Patreon. If you have questions or want to dive deeper into this subject, don't hesitate to join the Discord server. All the relevant links are provided in the description. I would like to thank all the Patreon members for their amazing support. I'd also like to thank Brilliant, the sponsor of this video. If you're interested in topics that blend math and programming, but find them a bit intimidating, Brilliant is the perfect place to start. Brilliant offers accessible and engaging courses on a wide range of scientific subjects, including math and programming. Their hands-on, interactive approach makes learning not only enjoyable, but also highly effective. Each activity is complemented by real-world examples that make the concepts more tangible and easier to grasp. The focus is on understanding principles and formulas, not just on learning them by heart. Plus, the app lets you do your daily practice from anywhere, making it even more convenient. Check out the link in the description to get 30 days of free access and 20% off the annual subscription.